Greetings, AP Chemistry students. This is Mr. Harper with the second episode of the summer podcast, okay? And in this episode, we're going to venture into Chapter 3, and we're going to talk about what's in a chemical name and all the rules that go along with naming different chemical compounds, okay? Now, as we go through this podcast, you will find it useful to have your list of common ions in front of you because we're going to use that as we go through and talk about how to name different substance. So here we go, okay? Before we go into naming rules, I want to talk about a chemical formula and what they tell us about a chemical, okay? So here we go. First, we're going to consider here a couple different molecular substances. Now, when I use this term molecular substance, what that means is that the smallest unit of that substance is a molecule, okay? So here we go. Let's consider here this first thing right here, O2. This is actually the chemical formula for oxygen gas, okay? Now, if I ask you on the quiz we're having here on the first day of school or on the test we're having here on Friday, after school begins, and I ask you what type of matter here is this substance O2, of course, you're going to tell me that this is an element, okay? Oxygen gas is an element, okay? But you're going to notice here that if we look at this chemical formula, what this tells us is that oxygen atoms do not exist separately from each other, okay? In the oxygen gas that you and I are both breathing right now, the oxygen exists as a diatomic molecule, okay? This formula tells me that every molecule of oxygen consists of two oxygen atoms that are joined together. Okay, so the symbol here tells me the element, and the subscript tells me the number. There's two oxygen atoms joined together by covalent bonds. Okay, we'll talk more about what covalent bonds are here later on when we get to the bonding unit. We'll talk about the shape of the molecule and that sort of thing. Okay, that's just a little bit of review for you from earlier in the year. Now, something I should point out here really quick. I'm throwing this word molecule around, and this is a very commonly misapplied term, believe it or not, okay? So when I say this word to you, molecule, okay, what I'm talking about is a particle, a unit of matter, okay? But what this actually means, okay, is a molecule is two or more atoms, okay, that are joined together by covalent bonds, okay? Now, covalent bonds, this is specific, okay, to covalent bonds. Covalent bonds are the ones where electrons are shared. You may remember from last year, okay? So this substance right here, O2, that is the element oxygen, okay? Let's look at this guy down here. This, if I were to ask you what type of matter is this right here, this is a compound. And the reason why this is a compound, okay, is because the molecule is made of more than one element, okay? If we look here at the formula, what this formula says is that we have one oxygen and we have two nitrogen atoms that are joined together to make this molecule, okay? Now this compound here has a name, and I'm going to get to how you name these, but this is called dinitrogen monoxide. That is the systematic name for that compound, okay? So these are some molecular substances. Let's look at a couple of different things. Ionic substances, okay? Now, ionic substances differ from molecular substances in that the smallest unit here in an ionic compound is called a formula unit, okay? Now, these are different from molecules because in a formula unit, okay, you have two or more ions, okay, that are held together by ionic bonds, okay? Now, it's a subtle distinction, but it's one that you should take note of, okay? Because there's some tricky nomenclature in there that can throw you off if you're not very specific about what we're talking about, okay? So here's two examples, okay, of different ionic substances, sodium chloride and aluminum bromide, okay? Now, let's look at what these formula tell us about these two substances, okay? If you look up here again at the molecular formula right up here, what this tells us is the composition of the molecules that make up this substance, okay? So in every molecule of oxygen, there are two oxygen atoms. In every molecule of dinitrogen monoxide, every particle of dinitrogen monoxide, there are two nitrogen atoms and one oxygen atom, okay? In sodium chloride, you never see isolated units of one sodium and one chloride ion, okay, that are put together and separate from other sodium chloride ions, okay? They always exist in something called a crystal lattice or a matrix, okay, which is kind of similar to this picture right here, okay? Actually, this depicts a slightly different ionic compound called lithium chloride, LiCl, okay? Where here these yellow spheres represent lithium atoms, okay? And these green spheres represent the chloride ions, Cl minus ions. Now, you can tell here, guys, that we don't have a separate lithium and a chloride, together separate from others. These are actually all mixed together. So we have a kind of a repeating pattern here, okay? We have a chloride ion, and then a lithium, and then a chloride, and then a lithium, and a chloride, and a lithium, and a chloride, and a lithium, and a chloride, okay? There's this matrix where if we look here, if we consider this one lithium ion, this is completely surrounded by a bunch of different negative chloride ions, okay? If we consider this chloride ion right here, it is totally surrounded by a bunch of positive lithium ions, okay? So if we consider ionic compounds, they have a different composition because they don't exist in isolated formula units or isolated molecules. You always have the positive negative ions here mixed up in that lattice kind of structure, okay? So if we look at the formula of an ionic substance, what that tells us is the ratio of the ions that make up that substance, okay? So if we look here at the sodium chloride, what this tells me is there's one sodium for every one chloride ion in that compound. If we look at aluminum bromide, okay, there's one aluminum for every 3 bromide ions in the compound, okay? And again, what this formula represents is it's like the smallest reducible number, okay, that you can have of the different ions that make up the compound. So, always the ratio of the ions occur in, okay? That's what this formula means. So keep those distinctions in mind as we talk about these different kinds of substances today, okay? Let's move on to naming, okay? I was throwing around here in the little introduction some different, chemical names. I want to teach you guys how to arrive at those names and how to write in this podcast formulas for different compounds. We're going to consider ionic compounds first because they're easier, okay? Ionic compounds always, all the time, always form from one or more positive ions, okay? These are called cations. We'll talk about why they're called cations actually towards the end of the year, okay? And they're made from one or more positive ions and one or more negative ions, which are called anions. These words, cation and anion, are important vocabulary words you guys should know, okay, when we get back to school, okay? The way that my chemistry teacher taught me is we look at this term cation. If we want to write it like this, we can write it like this with a little positive sign in there, okay? So cation, the T is like a little positive sign. We know the cations there are positive. It's kind of a silly way to remember it, but it works for me, okay? Now, why do ionic compounds form, guys? The reason why is simply because oppositely charged ions are attracted to each other, okay? So, for example, let's consider the most common ionic compound you guys have experience with, which is table salt, sodium chloride, okay? This substance, sodium chloride, is made up, if we just consider one formula unit of sodium chloride, we have one sodium ion and we have one chloride ion that are attracted to each other, and they form this unit, sodium chloride, okay? The reason why that whole thing forms is just the attraction between oppositely charged ions. And you may ask me when we get back to school, Mr. Harper, why is it that these ions are attracted to each other? And the reason is just because they are. The question of why do positive and negative things attract each other, that's actually one of the great mysteries of science. We don't really know, okay? But it's important to know that, if we have 2 sodium ions that get next to each other, these will not form a compound because they do not attract each other. In the same way, 2 chloride ions that come out next to each other, they will not attract each other. They do not form a compound, okay? Only oppositely charged things attract, okay? Now, the other thing that's going to be important as we talk about naming and writing formulas for ionic compounds is to realize and to remember that when we form the compound, okay, opposite charges always have to kind of cancel each other out, okay? Ionic compounds overall are neutral, okay, meaning that the positive charges and the negative charges balance each other out, and the total charge in an ionic compound is always going to be 0. Okay? For example, if we consider sodium chloride, here, in this unit of sodium chloride, we have one sodium and one chloride ion. Okay? This ion here has a positive 1 charge. This ion here has a negative 1 charge. When these two things come together, positive 1 and negative 1 add up to 0. So overall, this entire compound right here has a charge of 0. Okay, now in the same way, if we considered something like calcium oxide, okay, the calcium ion has a 2 plus charge, the oxide ion has a 2 minus charge. When these two ions come together and they form calcium oxide, positive 2 and negative 2 add up again to 0. Okay, so all the time, when ionic compounds form, the opposite charges of the ions that make it up will always add up to 0. This is another reason why an ionic compound always has to consist of a positive ion and a negative ion, and they always are occurring in equal abundance. Okay, or I should say not necessarily equal abundance, but stoichiometric abundance. Okay. Now, when we name ionic compounds, here's the system, okay? It is always named first for the positive ion, okay, called the cation, okay? And then second for the negative ion, which is called, again, the anion. Always we name the cation first, then the anion follows, okay? Now, for example, if we name this thing right here, NaCl, this is, again, sodium chloride, okay, right here, sodium chloride, because it's made from one sodium plus ion and one Cl minus ion here that are put together. Now notice, guys, when sodium goes from the element sodium to sodium plus, the name of the ion does not change. This turkey right here, Na plus, is just called the sodium ion. However, if we have Cl with a neutral charge, this is called chlorine. Cl minus is called chloride. Okay? Now, this is an important nomenclature thing, guys. When an atom, or an element, a neutral element here, gains electrons and forms an anion, like this, Cl minus. To go from Cl to Cl minus, this baby had to gain an electron, okay? When that happens, okay, so make it kind of visual, I'll write it down, okay? We take the thing here, the chlorine, okay, we scratch the turkey off, and we slap on an ide, okay? So there we go. That's how we get that chloride name. You're going to see it's just kind of a similar system going all the way around. Okay, if you look here at this next one, for the sake of argument, AlCl3, this is called aluminum chloride. Okay. CaBr2, this is called calcium bromide. Okay, now again, the way we got that, okay, calcium here is a 2 plus ion. Here we have, also here in the formula, we have, if we read it here, it says we have 2 bromide ions, okay, so we got a Br minus and a Br minus. The way we get this name bromide, again, is because the neutral element Br, bromine, okay, is spelled like that, but when that forms the ion Br minus, okay, we're going to scratch off that ene there and slap on an ide, okay? So it becomes a bromide when it forms the ion. So this is calcium bromide. This baby right here, the last one, okay? This is composed of a nickel 2 plus ion and an O2 minus ion, okay? That baby is going to be called nickel oxide, okay? That would be the name of that compound right there, okay? Now notice, if we consider all these compounds, okay, I'll just write this out here really quick, okay? So aluminum, okay, here is a 3 plus ion, and then we have 3 chloride ions, okay? Notice that for each of these compounds, the overall charge adds up to 0, okay? Here in aluminum, okay, aluminum is a 3 plus ion, or aluminum chloride here, aluminum is a 3 plus ion, then we have 3 chloride ions in the compound, each one has a -1 charge. If we have 3 ions, each of which that have a -1 charge, overall, we have 3 negative charges, we have 3 positive charges, so the total charge is 0. In calcium bromide, the calcium is a 2 plus ion, each bromide is a 1 minus, so we have 2 negative charges and 2 positive charges. That again adds up to 0, okay? And this last one here, nickel oxide, okay? The nickel 2 plus ion has a positive 2 charge, the oxide ion has a 2 minus charge, altogether that adds up again to 0, okay? There we go. So that's how we name ionic compounds. Now notice, guys, even though we had in aluminum chloride 3 chlorides, and calcium bromide we had 2 bromides, we didn't specify how many of each of these negative ions we had in these compounds, okay? In ionic compounds, you don't do that. That's just a convention because all chemists have their ions and their charges memorized, as will you by the end of the summer, hopefully, okay? Now, so those were pretty easy cases back there, all right? Now, there are more complex cases. Like, for example, right here, we have two different iron compounds, okay? Fe, by the way, this is the element symbol for iron, okay? So here we have FeCl3 and FeCl2. Now, what's different between these two compounds is obviously the number of chloride ions, but also the charge state of the metal ion. You will recall from last year that once in a while you can have a metal or some other ion that has different possible charge states, okay? There's more than one way when we're naming these babies that we can specify the charge state, okay? For example, let's look here at FeCl3, okay? We see here that we have 3 chloride ions, each of which has a -1 charge. So if we do a little bit of critical thinking here, you can also figure out that in order for these 3 negative charges to cancel out and overall for the compound to have 0 charge, this iron has to have a +3 charge. So it has to be a 3+ ion, okay? In a similar fashion for FeCl2, this has got 2 negative charges or negatively charged chloride ions, so this must be a 2+ ion. And again, guys, this is a kind of a weird symbology we have here in chemistry. I say this is a +2 ion or a 2+ ion. I use those things kind of interchangeably, but when we're talking about charges, we always put the magnitude, the number first, and then the sign. So 2+ ion, okay? This guy's a 2+, this is a 3+, okay? Here's how we specify that these have different charge states, okay? The most common way is like this. This iron here has a charge of +3. So when I name this baby, I can say this is iron 3 chloride, okay? Now what did I just do? I specified the charge using a Roman numeral, okay? That is the most common way to do it. By similar extension, this guy down here would be called iron 2 chloride, okay? And there we have it, okay? That's the more popular modern system for specifying charge states. Now, 2 and 3, are the charges that iron can have, but some things can have a bunch of different charge states. Like, vanadium's one of those weird elements. It can be a 2+ ion, it can be a 3+ ion, it can be a 5+ ion, whatever, okay? There's a lot of different charge states vanadium can have. A lot of different transition metals can have more than one possible charge state, okay? Now, if we're looking at something, though, there's another way we can do this too. If we're looking at a positive ion that can only have 2 different charge states, okay? Iron's one of those. It can be either 2+ or 3+, okay? I can use a different suffix to specify the high or the low charge state, okay? In this case, I could call this ferric chloride. And I could call this ferrous chloride, okay? Now, where did that come from, okay? The ic means the higher charge state. The us means the lower possible charge state, okay? So, FeCl2 is ferrous chloride. FeCl3 is ferric chloride, okay? In a kind of similar vein, okay? Say we're considering these two compounds here, CuCl and CuCl2. If I wanted to use that kind of older style of nomenclature to name these babies right here, okay? This copper ion here, we can tell, has to be a +2 charge. This copper ion here is a +1 charge, okay? I would call this baby here cupric chloride. I call this baby here cuprous chloride. Okay? Now, you're going to ask me, well, Mr. Harper, where on earth do you get these weird names? Like, where did ferric and ferrous come from? Okay, well, it actually comes from the Latin name for iron, okay? So Fe, the reason why the symbol for iron is Fe is because the Latin name for iron was something like, I think it's spelled as ferrum, and for copper was cuprum. So that's where these weird symbols come from for these elements, and we also kind of revert back to that if we want to use this older system, okay? But if you want a foolproof way to name these, stick with the Roman numeral fashion. That's kind of the easiest way, but also understand that if I say ferric chloride, I'm specifying the higher charge state of iron in that compound. Okay, so here we go. Let's talk about how to write formulas from a name if we're doing ionic compounds, okay? This kind of is two steps, okay? First is identifying the positive and the negative ions that are in the compound, and the next thing is to balance the charges, because we have to always remember that in ionic compounds, the total charge is always going to be 0, okay? For example, let's look at this one here, calcium fluoride, okay? You need to know your charges of your ions, okay? So calcium, we know, is going to be a +2 charge, okay, 2 plus. Fluoride is an F minus, okay, which is what you don't want in chemistry. Now, in order to make a good ionic compound, in order for it to be a correct formula, the total charge has to be 0. Okay. Now the easiest way for me to do that is, okay, well, if I have calcium is a 2 plus ion, how many 1 minus ions would it take to make the compound add up to 0? And you can see that if each fluoride has a -1 charge, we would need 2 of those to go with every calcium ion. So the formula for calcium fluoride is going to be CaF2, okay, like that. That's kind of the logical way to do it, okay? So, okay, you just kind of like, make the charges balance out and add up to 0, okay? But, say for example, we get to the AP test or one of my tests for example, and you stress out and you can't think and you don't remember what to do, or you're having a hard time thinking of it, okay? There's a shortcut way to do it. Notice here in this compound, okay, we have a subscript of 2 here, and we have a subscript here. It's understood there's a subscript there of 1. It's kind of implied. We don't write it there. There's only 1 calcium ion, but it's implied that it is there, okay? Now, let me go back. Okay? Now, the easy way to figure out the formula of an ionic compound is like this, okay? Here we have a charge of 2 plus. Well, this 2 here becomes the subscript on the other ion when they form the compound, okay? This here is like having like a 1 minus. This here becomes a subscript over here, okay? So there we go. So this is calcium fluoride. I had another student, some time ago, elegantly termed this the flippy thing, okay? So if you want to remember, remember it like that, that worked for some people. They call it the flippy thing, okay? Where this charge flips down and becomes a subscript here. This charge flips down and becomes a subscript here on the other ion, okay? Now, for simple ions like this that are derived from only 1 atom, we call them monoatomic ions, okay? The easy way, if you don't want to, memorize them explicitly, is to look at the periodic table, okay? You guys should remember here that this group right here is group 1A, also called the alkali metals. This group here is called group 2A, or the alkaline earth metals. Every element in this group right here has 1 valence electron. Every element here in this group has 2 valence electrons. To achieve a full outer valence, these 2 groups of metals will easily lose their valence electrons. All these guys here will lose 1 valence electron, and hence group 1A, these are always going to have a +1 charge, okay? Group 2A, these guys are always going to have a +2 charge. In a similar fashion, over here, this group right here, the halogens, these have 7 valence electrons. They always want to gain 1 more. So these are always going to have a -1 charge or a 1 minus charge. These guys here, okay, are going to have a -2 charge when they form ions. And these guys, when they form ions, will have a -3 charge, okay, and etc. So your periodic table will tell you the charges of simple ions if you remember how to use it. Okay, let's look at one that's slightly more complex, aluminum acetate. Aluminum ion will form a 3 plus ion, okay? Or aluminum will form a 3 plus ion. Acetate, this is an example of one of your polyatomic ions that you have to memorize. There's several ways you can write the formula, but here's my favorite way. It is CH3CO2 minus, okay? Now here's the thing you have to remember. This whole thing right here is a polyatomic ion. These atoms here behave as a unit. This whole thing has a charge of -1, Okay. Now, if we look at here, we have, a 3 plus ion here. Each of these is a 1 minus. We can easily see that we need 3 of these guys to balance out the positive charge on this aluminum. So if I was going to write the formula of aluminum acetate, here's how I would do it. I'm going to have 1 aluminum, and I'm going to have 3 acetates, okay? Now, when I have a polyatomic ion, the way to say that I've got more than 1 of these guys is I'm going to slap that whole thing in parentheses, okay? And I'm going to write a 3 down here. This says 3 of this whole thing that is here in parentheses, and then just, of course, 1 aluminum. There we go. Now, notice, for calcium fluoride, we did not do that for the fluorine because that is not a polyatomic ion. We only do that in the case that we have polyatomic ions like acetate, okay? So there we go. Let's do a few more examples, and here's where you guys can do some practice. What I'd actually encourage you guys to do is pause the podcast here for just a second, and then try to work this out on your own, and we will then come back and do them together. Okay, so pause it. Okay, and we're back. Here we go. Aluminum sulfate, okay? In aluminum sulfate, here are the ions. Aluminum, of course, is a 3 plus ion, and sulfate, this is one of your polyatomic ions that you have to memorize. This has a formula as SO4, and the whole thing has a 2 minus charge, okay? But remember, this whole thing behaves as a unit. This whole group of atoms has a 2 minus charge, okay? Now, obviously, 2 minus and a 3 plus, they don't balance out, so we're going to have more than 1 of these guys, okay? The least common multiple of 2 and 3 is 6, okay? If I have 2 aluminums, I'll have a 6 plus charge. If I have 3 of these guys, I'll have a 6 minus charge. If I add those together, they give me 0, okay? So the formula for this compound would be Al2SO4, parentheses, 3, okay? Now again, if you want to try the shortcut, here we go. We can do the flippy thing, okay? Here the charge in the aluminum, goes down here and becomes a subscript of the sulfate. The charge of the sulfate goes down here and becomes the subscript here on the aluminum. And here we go. Aluminum sulfate is the answer. Either way, either the logical way or the shortcut way will give you the same result. Next, iron oxide, okay? Iron 2 oxide. What this says is that the iron has a 2 plus charge. The oxide, of course, is a 2 minus charge, okay? Now, if I just use some logic here, this is a 2 plus charge, it's a 2 minus charge. I only need 1 of these to balance out the charge in the iron, so the formula is going to be FeO, okay? Now here's a good point to point out, well, what if I do the flippy thing, okay? This charge goes down, becomes a subscript there, that charge becomes a subscript down there, I would get Fe2O2. Now, this formula shows the same ratio of elements as this formula does right here, okay? But by convention, whenever we write a formula, guys, we always going to do it in the lowest possible terms, okay? So we get this formula using the shortcut, okay? Now, notice that both these subscripts here are 2. They can both be divided by 2. Whenever we can divide these by a number and reduce it to a lower term, we're going to do that. So if I divide these both by 2, okay, that gives me FeO, and so there we go, okay? That's the formula. Iron 2 oxide, okay? Or iron 3 oxide, rather, okay? That means iron here is going to be a 3 plus charge. Oxygen is going to be a 2 minus charge on the oxide, okay? And the same way as we did aluminum sulfate, okay, to create our neutral compound, okay, I'll need to have 2 irons, so that's going to be Fe2, and then 3 oxides, okay, because each of these is a 3 plus charge, so 2 of them is going to be 6 positive charges, 3 oxides gives me 6 negative charges, they add up overall to 0. So that's going to be my formula for iron 3 oxide. Okay, last one here, cuprous chloride. Chloride, of course, we know is a Cl minus. Now, cuprous, that's going to be a copper ion. Now, copper can be in 2 charge states, +1 or +2. The us ending means it's the lower of the 2. So this would be a copper plus, and it's going to be SCuCl. And there we go. These are the formulas of these compounds right there. Again, if you guys have any questions, go back, rewind, and try to watch that turkey again. All right. Let's look now at the opposite case. Let's go away from ionic compounds and now look at things that are molecular substances, okay? So I'm going to call these binary non-metal compounds, okay? Now, binary means we only have 2 elements. I would show you guys the rules for naming things that are made of only 2 elements, because when you get more than 2 elements, it becomes a little more complex. For example, H2O. Okay? Now, first of all, let's look at how this formula is written. This is written H2O and not OH2, okay? There's a reason for that. By convention, guys, when we write formulas of non-metal compounds, okay, both hydrogen and oxygen are non-metals, even though hydrogen here is in group 1A. It's not considered to be a metal, okay? When we write formulas for non-metal compounds, the elements are always listed in order of increasing group number, okay? Hydrogen here, this is in group 1A. Oxygen here, this is in group 6A, okay? So that's why we write them in that order. That's kind of the rule we're going to adhere to, okay? Now notice here, guys, we look here at the formula. Again, the number of atoms, okay, in the formula is given by a number here. When we write the name, the number of atoms of each type is given by a prefix, okay? So if I was going to give water here a systematic name, here's what I would call it. We have 2 hydrogens, so I would say dihydrogen. And then we have 1 oxygen right here. So I'm going to call that mon for 1 oxide, okay? Now again, here's something you want to take note of. We changed the name here of the oxygen. It went from oxygen to oxide. We're going to use this ending, IDE ending, whenever we name a binary nonmetal compound. The last element always ends in the ide. Okay, so there we go. Dihydrogen monoxide. Mon telling me we got 1 oxygen. Dihydrogen saying we got 2 hydrogens. Now again, guys, we did not use prefixes like this for the ionic compounds. That's just done by convention. That's just the way it's done, and you have to remember that. But for non-metal compounds, we do use prefixes. Let's do some more. And it might be kind of useful for you guys to have your list of prefixes. Okay, so here we go. Here's some lists of prefixes right here. Okay, so if we have 1, this is going to be mono. Okay, if we have 2, this is going to be a di. 3 is going to be a tri. 4 is tetra. 5 is penta. 6 is hexa. 7 is hepta. 8 is octa. 9 is nona. And 10 is deca. Okay? And you probably won't need to know anything beyond 10. Okay, so there we go. Okay, so let's name these turkeys. Okay, so here we go. NO2. Okay, now you would think, in fact, that according to what I just told you guys about the rules, you would think this would be called mono nitrogen dioxide. Okay, the IDE ending again for the last element. Okay, mononitrogen dioxide. In fact, that's not what we call this. This is actually called nitrogen dioxide. Okay, it's just a convention of the naming that if the first element, there's only one of those atoms, we don't use the mono then. Okay, we only use it for, the second element in the string. Okay, so that's one thing you just kind of have to file away and write it down. Okay, you don't use the mono if on the first element. Okay, this is called nitrogen dioxide with the name. Okay, in the same way, okay, if we look here at this next one, this would be called sulfur. Okay, SF6. Okay, here this is fluorine right here, so it's going to be called a fluoride. Okay, and we have 6 of those babies. So if we look here in our prefixes, 6 is hexa. It's going to be called sulfur hex fluoride. And we put that whole thing together. Okay, in a similar fashion, we look here at the next one, N2O5. We have 2 nitrogens, so we call that dinitrogen. We have 5 oxygens. The prefix for 5 is penta. So it's going to be pentoxide. Now notice what I did here, guys. I took the A off here. We had that contraction. If you have 2 vowels that are running into each other, you're going to take the A off of the prefix here. So it's going to be dinitrogen pentoxide. Okay. Last one right here is CO. This is the dreaded carbon monoxide right here. A lot of people are putting detectors in their homes to detect carbon monoxide, a poisonous gas that will replace the oxygen in your lungs. Okay. There we go. Those are some examples of how to name covalent binary non-metal compounds. Okay. Now, let's go and look at some writing formulas from names, okay? In the same way that we did before, okay, carbon dioxide. There's no prefix here on the carbon, so that says only one CO2 right there. For the dioxide, we have two oxygens. If you look here at the next one, germanium tetrafluoride, okay? Germanium, the symbol for germanium is the Ge, tetrafluoride, okay? So we have F is the fluoride. Tetra means four, so we have GeF4, okay? Last one, we have diphosphorus. The symbol for phosphorus is P. We have two of those turkeys. P2 pentoxide is P2O5. Okay, there we go. Oop. Okay, guys, evidently that is the end of the PowerPoint that I had for you guys today. I forgot that was the last slide. Okay, so those are some rules and some guidelines for naming different kinds of compounds. Later on here in the month, I will post a review podcast of all this stuff with some things to quiz you, okay, for how to name and write formulas of different kinds of compounds. There will be a few problems of this type on the quiz on day one, where I'm going to ask you guys to name some ionic compounds and write the formulas, and some covalent compounds and write the formulas. So there you guys have it. I hope you guys are having a nice summer. Until we meet or talk or podcast again, I hope you guys are having a good time, and I will talk to you all later. Hasta la vista.